Alright, so in this video we're doing a deep dive into the vision transformer. So the recent advances which involves like multimodal model like Polygema. So those are like nowadays getting very much popular, where we can like pass a text along with the image, and then based on the prompt we can like get certain outputs, right? So the backbone of this multimodal models, which involves image model also, the backbone is the vision transformer. So in this video, I wanted to take you through the very basic concept of vision transformer, how the different architecture works in case of the vision transformer, how we can apply the vision transformer in terms of the image, where we will see like how we will divide the image into several patches, then apply the multi-head attention mechanism, and in the end we will also go through detailed from scratch code implementation using Pytorch. So this is what I have in store for you in this video. So before going into the vision transformer, let's go through the CNN architecture and what are the demerits which we generally try to address using a vision transformer, right? So you know what this CNN architecture looks like, but in case you are not aware, I have a full deep learning with PyTorch playlist where we have gone through very much in depth how the CNN works and also the deep learning mechanism works, and along with the code. So I will also put a description of that series link in this video description. Now let's go through what basically a CNN is, right? So in terms of CNN, we have the input image. So those on top of that input image, we generally try to classify that image into several classes, like one of the several classes. Like for this example, you can see like we have an input image which is of this image, and then we try to predict whether that is a mammal or a fish, right? So that image which we use as input, on top of that image we run a convolutional layer, and then also we add the nonlinearity, and then we also add the pooling layers, and in the end we add a fully connected layer to do the classification, right? So this convolutional layer what we have here, that is nothing but it runs a kernel or a filter on top of the image, and based on that it tries to extract the features from the image, which will then be used for the downstream fully connected layers to do the classification, right? So if you just take an example, like we have this kernel, so that kernel we run across this image. So first we put here, then we do element wise multiplication, and then we do the sum to get a single value for this whole patch of the image, right? Run through the filter, and then we kind of populate the subsequent phases of the output by using this kernel, right? Now the drawback of this CNN architecture is that this feature extractor or the kernel what we have, that is very small in terms of the image. So if you take an example which image of size of 224 cross 224, generally we run a filter of size of 3 cross 3, right? So this 3 cross 3 is very small if you compare with the image that we have, right? So and the features that are being extracted, that generally are like local features that we try to capture using this kernel. So the global context is kind of missing if you are implementing a CNN on top of this image. So in terms of global context, what do I mean by global context is that pixel which is present here may not be related with the pixel that is present here using this architecture, but using vision transformer we try to capture the global context of the image, and if a pixel which is present here has a relationship with a pixel here, so that we will try to capture using the attention mechanism using in the vision transformer, right? So that is the architecture that we have in case of CNN. So this we generally also can tackle by stacking multiple layers of convolutional network, but vision transformer is kind of a more better approach if you want to capture the global context of the image, right? Now, before going into the vision transformer, let's do a quick recap of the transformer architecture and how the attention mechanism works, right? So we have this famous architecture from the attention is all you need paper. So that paper introduced you to of the architecture which is like encoder. So this is the encoder side, and we also have the decoder side, right? So there are several models which are based on either like encoder architecture or the decoder architecture. In the encoder architecture, we have models like BERT, and decoder side we have the famous GPT architecture, right? And we also have encoder decoder based models which are like T5. Multi-head attention is one of the thing which is kind of a building block of this encoder side architecture. Now let's go through this multi-head attention, right? But before going into the multi-head attention, we need to know what does this self-attention is actually is, right? So if you talk in terms of text data, so for an example, we have an input sentence, right? Like attention is all you need, right? So this is kind of the input sequence which we can think of. So there are five words which are present here. So that word can be also subdivided to create the tokens, but for the simplicity we assume that each of these words are a single token. So we have like 5 tokens in this input sequence. Now, using the encoder side and using the attention mechanism, what we try to establish is the connection or the relationship between uh, each of the tokens to the other tokens that are present in this input sequence. So for that, what we do is we introduce three of the learnable matrices, which are like WQ, WK, and WV. So this input we generally denote as X. So the input sequence is X. Then what we do is we multiply the X with this WQ, WK, and WV, and we get the query key and value matrices, right, with this methodology, right? So once we have that, what we do is we apply the equation of the attention mechanism. So there are two parts to this equation. So one of them is like this part, and then where we calculate the dot product between the Q and K transpose. Then to reduce the variance of this dot product, we divide it with the dimension value of the embedding, and we get this part. Then we multiply with a value vector to get the final embedding, which is much more context aware and contextually rich, right? So as I mentioned, like we are taking this example, attention is all you need, where we have the sequence length as 5, and k is nothing but the embedding size, right? So if each token is represented with a vector, now that vector will be a multidimensional one. So the size of this generally in the attention is all you need paper was 512. So the k value is 512, right? Do is we get the query matrix, and that we do a dot product with the k transpose just to match the inner dimensions, and then we divide it with the square root of k, and we get this n cross n vector after taking the softmax of this whole dot product, right? So this is attention based matrix what we get as a first step. So then in the second step what we do is we do again a dot product between this n cross n attention based matrix with the value vector or the value matrix, and we kind of do this n cross n multiplied by n cross k. So we get an output of n cross k, which is the attention based embedding which we get as output of this whole self attention mechanism. So we can see like the attention scores are present here, which where the values are high, that means those tokens are related between each other, so that we can see using this matrix, right? So once we have that matrix, what we also do is we kind of apply the multi-head attention, where what we do is we get the input, then based on the input we get the query key and value, and then we kind of subdivide this each of these query key and value matrices like q1, q2, and q3, and similarly for the k and the v vector. Then we apply the attention mechanism using the previous method which we talked about, and we get the attention heads for each of these matrices, right? Which are like H1, H2, and H3. And then we kind of concatenate and multiply with the output learnable matrices to get the multi-head attention, right? So this is what a multi-head attention works. The crux of this multi-head attention is this. If you want to do a deep dive, I would request you to go through the video which I will be giving the link of that video in the description of this video, right? So once we have the multi-head attention, so then what we can do is we can now talk about what this VIT is, or the vision transformer is. But the challenge comes here, how we will implement the multi-head attention in terms of the image. So if you break down an image, so image is nothing but three matrices, which are like red, green, and blue, stacked on top of each other, and that is kind of a representation how a machine sees a image, right? Now, how we can apply the attention mechanism to these images, right? So for that, we need to do a few of the series of steps to apply this multi-head attention on top of this image, right? So those series of steps are like this. So it has like 5 steps which you can think of. First, we will apply patches on the image to create small patches out of those image. Then we add a CNS token. So this CNS token is again similar to the concept what we have been doing whenever we are using a bird-based embedding, where we use the CNS token, then using that we do the sentence level classification, and we kind of assume that the CNS token is kind of representation of the full sentence, right? So here what we will do is we will assume that the CNS token will be the representation of the whole image, right? So once these 2 steps are done, then what we do is we add the positional embedding. So we need to capture the sequence of the patches of the image. So we add additional positional embedding. Then we pass it through the multi-head attention, and in the end we will add a multi-layer perceptron to do the classification task, right? So first things first, now how do we create the patches of the image, right? So we have this whole image. So here we can uh, apply certain techniques, like we can apply a convolutional neural network or a multi-layer perceptron to create patches and divide this image into several patches, right? So what we can see, like we have divided this image into 9 patches, and those patches are present here. And then once we add the CLS token, we now have the linear projection of the image in terms of patch embeddings, and also we add the CLS token. Now to capture the sequence of these patches, what we also do is we add the positional encodings. So these positional encodings are slightly different. What we use in the attention is all in with paper. Here we put learnable parameters as positional embedding, where each of the patch will have the corresponding positional encoding to represents the patch's actual position in the image. So once we have that, we add the positional encoding to this patch embeddings along with the CNS token, and we kind of get a representation of the image which is now ready to be passed to the multi-head attention phase, right? So to this transformer encoder architecture, where we apply the multi-head attention. So here we generally implement the multi-head attention and the other mechanisms where we have the residual connections, the layer normalizations. So those things we have inside this architecture, and then we use this CNS token as a representation of this full image, and then we pass this CNS token to the multi-layer perceptron head, where we will get the logic as outputs, and then we can do like multi-class classification or a binary classification using those logics, right? So this is what the architecture is. This is a very straightforward architecture. So once we go through the code, you will get more clarity how this is actually working. Now let's discuss how we can calculate the size of this patches, or the number of patches that we generally have in terms of the image size, right? So for the example, which I will also go through in the coding part, so there we have the image size as 28 cross 28, which is like nothing but the height and width of the image. So patch size are 4. So based on that, we can calculate the number of patches using this formula. So what we can do is we can divide this 28 by 4, and then also we can divide the same for the width. So this is for the height and this is for the width. So what we get is this 7 cross 7, which is nothing but 49, right? So the simple formula is we can divide the image size. So this is like image size, then we divide by the patch size, and then we do a square. So the square is for each height and width to calculate the number of patches that we have, right? So once we have this 49 patches, what we do is we add the CLS token to this. So this CLS token plus 49 patches, we get the 50 patches what we have at this point of time, right now what we do is we add the positional encoding on top of this, and then we pass it to the multi-head attention phase, right? Now the shape of this is quite essential. How this shape is actually working, that we need to understand. So uh, to calculate the shape, so we already calculated the number of patches. Now the shape of the input to the multi-head attention is like the batch size, then we have the number of patches, and then the embedding dimension, right? So this is what the actual uh, shape of the input to the multi-head attention. Then we kind of add this multi-layer perceptron, and using the CLS token, we do the classification of the input image, right? So this is on a high level, and I hope this gives you a good idea of how the architecture of vision transformer is working. And now let's go through how the coding mechanism is working, which will give you more clarity on this architecture. Alright, so now let's go through the coding implementation of Vision Transformer. So we will do it from scratch. So we will use Pytorch as a library, but we will build the architecture of the Vision Transformer from scratch, and we will try to do the classification on top of Omnis dataset, which is a 10 class classification, and based on that we will try to build a classification model, right? So first of all, we will import a few of the libraries which are required. Then the important data set preparation step is required. So I have a playlist of deep learning with PyTorch. So if you are not familiar with PyTorch, you can go ahead and look into that playlist for a deeper understanding of how PyTorch works and how you can build deep learning based models using PyTorch, right? So few of the steps which are required, like you will read the data set, create validation set, then create custom data set class through which you will create the train and validation data set, and after that we will create the data loaders, right? So this is a data set which I am loading here in the train df. Then we are creating the train and validation df using the train test facility of scikit-learn. And after that, what we are doing is we are creating a custom class, so which will like inherit from the dataset class of PyTorch, and it will enable us to create the data loaders using this class, right? So I have used two transform function here, which you can see here. One of them is train transform, another one is a valid transform. So in the train transform, we have few additional transformers, which is like random rotation, which we will use during the batch generation, and based on that we will do the data augmentation to create new set of images, which is not part of the validation set, right? So then what we are doing here is we are creating a length function and also the dunder get item, which will create the image and label pairs, and using that we will create the data loaders, right? So here we are creating the data sets. You can see the train ds and the validation ds. We are looking at the shape and also the number of classes that are present, right? So then using a batch size of 512, we are creating the train loader and the validation loader, and we are just looping through the train loader, looking at the one batch and seeing what are the shape of the images. So you can see that there are 512 number of records in one batch, and the shape is, this is a channel number. So one is because it's a black and white image, then there is height, and then there is width for each of these images, and corresponding we have 512 labels for this each of the batches, right? So then what we'll do is we will start creating the vision transformer from scratch. So here we have the parameters which we are initializing, the num class, the patch size, The image size is, we are already aware, 28 cross 28. So we know the in channels are 1. So the number of heads that will be created for the multi-head attention encoder blocks. So there will be 8 encoder blocks which will be stacked on top of each other. And then we have a dropout for doing the dropout regularization. Then we also mentioning what is the hidden dim, and also the activation function is GELU. So that is present in the paper itself. So we are just borrowing that idea. Then we are mentioning what are the number of encoders. So here we can see like the number of heads and the number of encoders are also present. So while building the multi-head attention, so there would be 8 heads, and for each of the encoders we will have 8 number of encoders which will be used to create the multi-head attention and create the final output. Then we have the embedding dim, which is the embedding dimension which we have talked about in the last section of the architecture review. And then we also have the number of patches which we calculated using by dividing the image size by the patch size, which will then we are squaring it, so we are getting a value of 49, and the embedding dimension is 16 here, right? So these are the parameters which are required. Then what we are doing is we are creating the patch embedding class, which will actually divide the images into patches, and then it will like add the CLS token and also the positional encoding. So the first part is where we are creating the patches. So you can see this is where we are initializing the patch. So here what we are using is we are using a convolutional layer. So you can see the in channels, we know like that value is 1. Then we have the embedding dimension, which is the output channels, so which will be used as embedding dims for each of the patches, right? So then we have the kernel size. So this is important. So where kernel size is equals to patch size. So if you just do a visualization here, so if this is your whole image, and these are the this is the full image, right? And we are mentioning the stride is also equals to patch size. So we have, if for an example, if we have a 4 cross 4 patch which is like this, and the image is also like this. Just let me expand this. So what it will do is at first it will place uh, the convolutional kernel here, then it will extract the features of it, and it will create a patch using this, right? So then what we are mentioning is we are mentioning the stride is equals to the patch size. So next time the kernel will be placed here, so using which will again create a patch here. So first patch was this, the second patch is this. So in that way it will keep on creating the patches on using this kernel, and it will then like stack those patches, and it will like, then what we'll do is we will flatten those to create a two-dimensional representation, and we will get each of the patches from this image, right? So I hope this is clear to you. Then what we will do is we will create the CLS token. So this CLS token will be where we are making it as learnable parameter. So you can see we are mentioning required square equals to true, and we are initializing with random values using this shape, right? So then we are adding the positional embedding, which is again initializing with random values, and we are mentioning that the required square equals to true. So both of this, the CLS token and also the positional embedding, are learnable parameters, and then we are also initializing the dropout with the dropout value, right? So then in the forward method implementation, what we are doing is we are getting the image, then using that image we are creating the CLS token, then we are passing the image to the patcher, and then what we are doing is we are doing a swap of the dimensions, right? So this will enable us to create the patches in such a way that first batch size is there, then the sequence length, which is in case of text or the textual representation or the sequence, we generally mention it as sequence length. So here this value would be number of patches, and then we will have the embedding dim, right? So previously the shape was like that size, then the embedding dim, and then the number of patches, right? So using this swap, using this permute function, what we are doing is we are bringing the number of patches as second dimension, and the embedding dimension we are pushing as a third dimension, right? So then what we will do is we will add the CLS token to this. We will just do a concatenation, and we will add the CLS token at the front of the patch embedding, and then we are adding the positional embeddings to the patch embeddings, right? And then we are adding the dropouts. So this is what we are doing here inside this class. So then what we can do is we can initialize this patch embedding model, and we can pass image to this, and we can see the shape of this, right? The batch size, the number of patches. So the number of patches was 7 cross 7, which is 49. Then we have added a CLS token. This is a CLS token, so the size becomes 50, right? And then we have the embedding dimensions, right? So this is all we wanted before we put this patch embeddings to the multi-head attention. Right? We'll create the vision transformer class where we will have the patch embeddings, the transformer layers. So we can see like we have the patch embeddings, then the transformer encoder layer. So we will create the individual encoder layer. Then based on the number of encoders, we will create this encoder block, right? So we are using the Pytorch implementation of this encoder layer. We don't need to do it from the scratch. So there itself we are passing all this embedding dim, number of heads, the dropout, the activation which is GELU, and also the batch first equals to true, and also we are mentioning normalize first equals to true. So all these things which are inside the encoder block, the multi-head attention, the layer normalization, the residual connection, so all those will be implemented using this two things, right? So then we are adding the multi-layer perceptron head, right? So this at first it will do a layer normalization, and based on the number of classes it will add a linear layer which will accept the embedding dims, and the output will be the number of classes, right? So here the number of classes are 10, so it will produce 10 outputs, and then we can take a argmax to get the label of that prediction, right? So this is the implementation of that. So then what we are doing inside the forward implementation, we are first adding the patch embedding blocks, then the encoder blocks, and also the multi-layer perceptron head. So while doing the multi-layer perceptron head, we can see like we are only passing the 0th index for the sequence length, which is nothing but this is the CLS token that we have. We will do a test of this. So we will pass the image to this model, and we can see we are getting an output of 512 cross 10, right? So this 10 is nothing but according to the labels that are present inside the data, right? So as we can see, if we just print out the first output, we can see like there are 10 values, and based on that we will take a argmax, and we can see this is the actually the label, which is like this is 0th label, this is 1 2 3. So for this image 3 is the label that we will select as prediction, right? The cross entropy loss and also the optimizer, and we will run this model for 10 epochs, right? So this is regular Pytorch stuff. We are also adding the validation data loader through which we will monitor the validation loss here. That is done, we can start making inferences, right? So using the model, we will put the model in the evaluation phase, and then we will pass the image to the model, and we will get predictions, right? So you can see like we are using the argmax here to get the predictions for each of the images, right? And then we can calculate the accuracy. So the accuracy is very low because I haven't done the fine tuning, or I haven't run this model for longer epochs, and also haven't done the optimization. So the idea is to show you how you can do this implementation and do it from scratch, just to take you through the concepts and how you can implement using Pytorch, right? So this is all I wanted to cover in this video, which is I hope you got a good understanding of all these concepts. Hope you like it. Share the content with your friends and colleagues. Thank you. See you in the next video.